Okay. All right. AB is a chord. Who can make me a definition of that one segment? We'll start with segment. What is it, Carly?
A segment that goes across a circle but is not the diameter.
Goes across.
Intersecting two points.
Endpoints.
Has two its endpoints are on the circle. How am I doing here?
That sounds good.
Yay!
Endpoints are on the circle. Okay, and I'm going to continue to use that symbol for circle. So just get used to that, just because I'd rather do that than write out. Okay. As opposed to maybe arc AB. What's an arc again? We talked about it last chapter. Okay.
Section.
Okay. Very good. So part of the circle, the actual curved part, if you need to remind yourself that it's curved, then write that word in there. Okay? We have types of arcs. We have major, minor, and the semicircle. Okay, how big is a semicircle? 180 degrees. Okay. What do you use to name? How many letters? 3 letters. Okay. So for an example, E, A, E, D, A. Let's just assume that, yeah, that's half. We'll just assume it is. So E, what was the middle letter?
B.
B, or an A, or
E, D, A.
Oh. Okay, bully. All right, and remember you can go either way, right? You can start with A, but the middle letter just tells you direction, right? Okay. All right, minor arc. What size is it? Okay. Yes, she did. All right, to name it, how many letters do we need? 2. You can use 2. You can use 3. If 2 is clear, use 2. There's no point in muddling that. But you can use 3. 3 does not automatically think it must be a big one. It's not. So, okay, so give me an example. Rachel. Arc DE is definitely smaller than 180. Carly?
DEB.
DEB. Okay, so those are 2 good examples. All right. Okay, major arc is more than 180 degrees. To name, you have to use 3 letters. Okay. So what? Assuming EA is a diameter, let's see. Give me one. Catherine?
ADB.
ADB sounds good. I'm running out of room. I got too tight here. Okay. And how about another one besides BDA, which is the same one? Kate?
EBD.
EBD? E to B to D definitely is. Good. Major. Okay? Very good. All right. Again, central angle, what is that? Let's look at the central angle. Do you remember we talked about that last chapter too? Angle, give me an example. DCE, right. And what's the definition of a central angle? Ellie?
The angle that starts from the middle of the circle.
Angle whose vertex is the middle of the circle?
Yeah.
Okay. Whose vertex is the center of the circle. And sides are what? Good. There you go. It's an awkward word to say, isn't it?
I don't like that
I
one.
don't want to get written or spoken.
Exactly.
Right, yes,
Yeah, it's a little awkward.
not right.
Okay. All right, any questions about the vocabulary? That's what we're going to get into. Shh. Chords and arcs, arcs and chords. Here we go. Okay, let's look, assuming that this circle is divided equally. What do we got? 1, 2, 3, 4, 5, 6, 7, 8 parts. How would we find the measure of, say, this central angle? 360, because that's all the way around the circle divided by 8. And what is that? That's 45 degrees. Okay? Remember the central angle, if that's 45, what else do you know? Anything about an arc?
It's a minor arc.
You mean it intersects the minor arc?
Yes.
Okay. What do we know about the measure of that minor arc? It's 45. The measure of the central angle, let's say, determines, so is the same as the measure of the intercepted arc. Okay. Intercepted arc is a huge thing this chapter. Here's kind of what I want to think about. If you have your two, let's see, rays here, if you would squeeze those together, that's the arc that would be intercepted. That's the arc that would, if you just put that together, that would pop out, right? So that's what I would call the intercepted arc. The arc in between your angle. You're going to have all kinds of intercepted arcs, not just with central angles. So you need to understand what arc it intersects. Could also be interpreted that same way. Okay, intercepted / intersect. In this case, are interchangeable. Ready?
How many interwords can you put in one?
I don't know. 3. Oh,
It's just
no. Okay. All right. So let's start with some theorems. Is that what's next? Is anyone hot? Here's my response to that. And imagination is a beautiful thing. You know, I've had squirrels on bushes before. All right. Theorem 12.4 and its converse. What's the converse to again? Switches what? If and the then get switched. Okay, so let's figure out here what we have within a circle or in congruent circles. Within a circle, congruent central angles have congruent arcs. Okay, that seems like a duh to me because let's say this green central angle, what does it look like? About 40 degrees? Okay, we're going to say it's 40. Okay, that makes arc AB how many degrees? 40. Okay, all right. Remember, if we have congruent central angles, that makes this red angle also 40, and that makes this 40 as well. Therefore, they are congruent. Okay. It seems like a no-brainer, but the problem is you're not always going to have the numbers to make it make sense. If you say these are in a circle, let's say you have, oops, I didn't make sure, diameter there. You have to have a diameter of about central angles. I got to go through the center. There's my center. Okay, these arcs, those angles are congruent, right? Why? Vertical angles. Okay, which makes this arc congruent to this arc, right? Okay, regardless of what number you could attach to it. Okay, so that's one of those things that you kind of have to look for, because what we're going to do is we're going to find the degrees of arcs, and then we might need to know the angles with it, may or may not. Okay, let's try an example here. Arc AB is congruent to arc DC. Okay, so somehow you need to mark that. Let's see, C, I'm assuming is right here. So this is congruent to this, all right? Now, they aren't really vertical angles. If you look really closely, they don't even look like vertical angles. But what does this give me without even further venturing into the problem? What do those congruent arcs give me? Rachel? Which congruent angles? Good job.
Angle B, angle C.
Right. Okay, so congruent arcs give me congruent angles, central angles, all right? Solve for X. Well, looky here. Here's AOB, here's COD. So I'm just going to move this statement down here, maybe. And I'm going to replace AOB with 3x plus 30. I'm going to replace COD with 5x minus 2. Because congruent meanings have the same measure. Those are the measures. And you're going to solve for X. What's X? Actually, 16. Good work. Okay. You get 2x over here. You get 32 here. X equals 16. Okay. So that's the kind of application. We don't have any numbers, so that's why we have to think, okay, I got congruent arcs. I got to have congruent central angles. So that's good to know that theory. And vice versa, if they told me these angles were congruent, these arcs would be congruent as well. Okay? All right. Here's another couple theorems and their numbers. Okay, within the circle or in congruent circles, congruent central angles have congruent chords this time. All right, well, central angles, COD and BOA are congruent. Okay, that automatically makes the chords right there, CD and BA congruent. Okay? Now, do we want to talk about why that would be? Let's get out of the circle a minute. Okay? Why would these be congruent? Anybody want to think about that one? Jessica.
Because the angles are congruent, so they're opposite.
Let's remember, if these are congruent, then those are congruent. Doesn't really count with two different triangles. But that was a good thought. Kelly?
Because, I just lost my train of thought. Okay, I'm just so excited.
I lost it.
What do you think, Kelly?
Because since the angles are congruent, that makes like the top, and then the radii are congruent, which makes an isosceles triangle, which makes them similar.
Similar, even better than that. Congruent triangles.
Because
Just spell it for me.
yes.
Right.
And then we'll say that.
You really wanted to say it, dang it. Okay. So that's the long story, but now that we know this, we can just go directly from congruent angles to congruent sides. Okay? Of those segments. Okay, vice versa. Also, if you have the segments congruent, the little central angles are congruent. All right, what about here? We got congruent chords have congruent arcs. Okay? So, chords make congruent arcs. Okay? So basically, if you got something congruent, that is going to give you something else congruent. All right? And vice versa with that one. So those are kind of hard to see. I'm not sure what happened to that, but anyway. Let's look at this diagram. Circle O is congruent to circle P. Okay. All these diagrams, all these theorems said in a circle or in congruent circles. How are circles congruent? What would you have to know about them? in order for circles to be congruent? Ellie?
They have the same diameter and form.
Right. Congruent circles would have to have congruent radii or diameters. Good job. Okay, so that's what you're assuming that it all congruent. Okay, that's what it says with just this piece right there. Okay, BC is also congruent. BC, DF. Okay. Now, try to use the theorems. What else can we conclude? All right, give me one thing.
Arc BC is congruent to arc DF.
Right? Why is that?
Because congruent chords have congruent arcs. And that was very uneloquent way.
That's okay. That works. Congruent chords have congruent arcs. That's you're right. It's not very eloquent, but it works. Everybody knows what you're talking about, so it's totally fine. Okay. All right. We've got the eloquence up here. We have to say it in our own words in order to go for it. Okay. Good job, Kate. Okay. Good. Why is that?
Congruent chords.
Okay. Yes. Congruent chords have congruent central angles. If you don't like the have, you could say yield. You like that? I like it too. It really makes more sense, but again, I'm okay with have. I really am. All right. This is whacked. Is it whacked on yours? Does it look like this?
Yeah, it does. Mine doesn't.
What does it look
I
like?
printed to OneNote. It's just doesn't have a scribble. Doesn't have an S.
Okay, well, let's just see. Okay, circle O equals circle P, so again, radii all congruent. That's what that means. OPC, OBC. Oh, that's not a central angle, so be careful. PDF, not a central angle, so be careful. Okay. What can you conclude? All right, so what can we conclude? We got all kinds of things we can go on and on and on. All right, Ellie Madeline, give me one.
The triangle inside of the circle EOC is. Wait, okay. The triangles are isosceles triangles, so that means BCO is congruent to DFP.
BCO is congruent to DFP. Very good. Because isosceles, triangles, blah, blah, blah. Okay, she said it a lot better than I did. So I can just mark them one hoop because now all four of them are congruent, right? If this was congruent to this and this was also congruent to that, they're all three congruent, right? And now they're all four congruent. Okay. So I don't know why I made those so large. Let me get rid of largeness there. Okay. All right, that was a good conclusion. Kate, you got another one? So the chord is congruent. Why is that? So we know their central angles are congruent. So BOC, we don't know that. So we need to conclude that first.
Okay.
Why is that?
Because the triangles
I'm gonna say- wait. Do we have congruent triangles? What? Angle side? Okay. I'll take it. Congruent triangle. Angle side. CTC. Okay. Now the central angles give us the chords. Okay. Congruent central angles give us. I'm just going to do this. Give us congruent. Congruent chords. Okay. What else? Go ahead.
Arc BC is congruent to arc DF.
Arc BC is congruent to arc DF because
Their chords are congruent.
congruent chords give us
Congruent arc.
congruent arcs. Good. All right. We got all kinds of things congruent here. Let's see. 2, 2, 1, 2, 3, 1, 2, 3. Okay, and I didn't even mark this one. Am I missing anything? Yikes. I think we covered about everything, didn't we? You all did a good job. Okay.
Let's see what it is. One.
Now, we are not going back to, are you serious? We got to prove this. But there's a lot of connections that y'all are making from way back, so that's fabulous. Okay? No, we don't have to. But that's kind of the puzzle thing that geometry does. That gives us that, which gives us that, which gives us that kind of deal. Most of the time, you all have enjoyed that, right? Okay. All right, so, no, you're not going to have to use the words. We're just using the words now just to kind of, yes, promise. Okay, right here, distance from a point to a line. Okay, here's a point, here's a line. Now, draw me the distance, the one line that would be called the distance. Here's my point. Here's my line. Draw me the one line that would be considered the distance between those two things. Just draw it. Now. All right, you got it. You did. I don't know. You didn't tell me what you were doing. Maybe you just aren't telling me.
Oh my God! Did I?
You gotta tell me something. Ah, there it is. You got me. Okay, yeah, that's it. All right. The distance from a point to a line is perpendicular distance. Okay? All right. Perpendicular distance. Now, that is never going to be spoken or written for you, but it's implied. Okay? Because otherwise we could all say, oh no, my distance is this way. Or no, it's this, or no, it's this. Those are all distances, so we have to agree, whoops, wrong one. We have to agree that the perpendicular one is really the distance. Get that? Alrighty then. Okay. Alright, so equidistant, what do you think that means? No, it's equal. Equidistant. Okay, what do you think it means? Two distances that are equal. That's right. Distances that are equal. Okay. That's the word. It's one word. Okay, so you're going to get that implication. You got that in this next theorem. Okay. Within a circle are congruent circles. Chords. Here's my chords that I'm talking about. These kind of greenish ones. Stop. Okay. I'm serious. Okay. Those chords that are equidistant. So see, they're from the center. Here's my center. Notice the perpendicular distance, and notice they are marked congruent. So that means that they're equidistant. Equidistance from the center. So if you took your center of your circle, I'm not going to draw your circle, you had a chord that looked like this, and a chord that looked like this. The perpendicular distance Now to make them equal, you did this. Okay, so now those are equidistant. The lines are equidistant from that center point. Yes?
So it's every distance, like if there's two distances in a circle, but they both be congruent?
If they tell you it's equidistant, yes, that's what they're telling you, that those distances are congruent. Yes. Okay. All right. And then the converse of that, if you know that the chords are congruent, we also know that the distances are congruent. Okay? Now, this is probably the hardest one, just because there's a lot involved. So it's easy once you get it. Yes, Emma?
Does there have to be like the right angle sign to be able to say that?
Yes. They will give you that though, usually. And then if you're drawing it, you should just like write that in there. Okay. So it says, what is the length of RS in circle O? Here's RS. Okay. Now, first you're going to look for, oh wow, there's a distance from this point to this that's marked 9. There's a distance, see the perpendicular, there's a distance from this point to this line that's marked 9. That means they're equal, right? Because they're both 9. So if this chord and this chord are equidistant, what do we know about RS? RS is congruent to PR. That's right. Okay. Well, I don't have PR, but I could get it, right? What is PR? 25, because it's twice 12 and a half. Again, that was just something that they told us. All right, so they're both 25. Okay, there's a lot going on. This gives you this, gives you this. All right, try the next one. What is the value of X?
Oh, I thought that was a quite a question.
That was a question about trying on your own before.
I didn't get that part.
I noticed. Okay. All right. So explain why X equals 16. Okay, using the theorem language. Go ahead.
X equals 16 because both the chords are congruent to each other because they're both 36. And
Very good.
And also distances, they're equidistant because of
Okay. Very nice. Equidistant.
those two words.
Those are beautiful words from that point center of the circle. I'm not going to say her words, but you did a nice job. Okay? Does that, everybody get that? It's not going to be hard, but it just seems like it's going to be involved. And we're going to quit telling you this piece on the next slide, I think. That's next. This piece is going to be an automatic, too. Ready? Oops. What's the radius? Oh, well, okay. Missed that piece. All right. Thank you. What is the radius? Okay, there's no radius drawn at this moment, right? So why don't you go ahead and draw it in there. And if you're smart, you'll draw it where you can do something with it, not just like, let me just finish this on up and I'll draw it like that. That's not a smart radius. It's a radius. There's a better place to draw it. All right? Let's see who's got it drawn smartly here. That's smart. That's smart. Go up there and draw it there, Rachel. You're drawing yet? Wait a minute. Everybody, that's good. Everybody get a chin. That's not so good. That's good. Not smart radius. No. Rachel, show us that's a smart radius, Lindsay.
That was the
That's a smart radius. All right, check it out. That's okay. You can move it over with your. All right. Where'd that come from? It was probably your finger or something. Okay, now, I didn't need to insult anyone by telling them they weren't smart. I was calling that radius smart. Okay, so why is that smart as opposed to, I got anywhere from, you don't have to claim these, this, or I got this. Why is that one smart, Ellie?
Because there's a right triangle, so you can use special triangle.
Praise the Lord. Well, I don't know about special, but you can use the Pythagorean theorem to find it, see? This is 18, this is 16. How are we going to find these? Let's call it radius. 18 squared plus 16 squared equals radius squared. What is that? Is that a...
It's not an it's going to be a rounded method.
All right, don't round then. Simplify your radical like smart geometry students. No, you are. Or some of you are. I'm just kidding.
Yeah, it's just coming out today.
I think I got it. Think you got it? Anybody? Go ahead. Okay, do we have any confidence in her when she starts out like that? No. Okay, let's say with confidence, girlfriend. Let's see. I feel like that's definitely 580, but 145. I know it's divisible by 5, and then it takes 5 times 29. I think you're good. Go Ellie.
Team Ellie. Yeah. Crawford.
Great, now she's starting with full.
Okay, we had a 5. We know a 5, right? Because it ends in 0. When we get the 5 in there, there's not a 25. So the 5 really doesn't do us 29. We recognize as being prime, so we're done. Okay, so let's see. Okay, so this is the last big one, and then we're going to put it all together. Okay, there's 3 that go here. Now look for a common theme. Okay, in a circle, if a diameter is perpendicular to a chord, then it bisects the chord at its arc. Okay, so we got a diameter, which remember is also a radius. Okay, if you got a perpendicular, you got your bisected base, your segment there, and your arc. Okay, check these words out. A diameter bisects a chord, then it is perpendicular to the chord. Okay, so we start with knowing this is a diameter and this chord is bisected, then we also know it's perpendicular. Okay, last one, and then they all go together. We start out knowing that the chord is perpendicular and is a bisector. So see, you got the chord being a bisector, the diameter, sorry. Something missing there. In a circle, the perpendicular bisector of a chord. Okay. The diameter happens to be the perpendicular bisector of the chord. So bottom line, here's what happens. If you have, we have perpendicular, chord perpendicular to diameter. In this case, it also could be just a radius hanging out here. Okay? We have the chord being bisected. What's the third thing? It wasn't on this third one, but it's the arc is bisected. Okay? So if you have 2 of those, you have automatically the third, basically. Okay? So if you have 2, you're going to have the third. You could have these 2, then you have this one. You could have these 2, then you have this one. You could have these 2, you could have this one. Okay? So they all go together. It's sort of like this one where if you've got this and this going together and the perpendicular, then you automatically have that. If you have that and the perpendicular, you automatically have that. So 2 gives you the third. Okay, ready to try some examples with that? Yes?
Why do you need the perpendicular, like the chord part? Because wouldn't the diameter always have the center of the circle on it? Like, why do you need that part?
In which one are you referring to? Yeah, and here's the thing. If it's not going to be, see, here's the bisector and the perpendicular. This is automatically going to be a diameter. That's what you can conclude from that. You know what I'm saying? Does that make sense? So you've got this going on, you've got this, and you've got this. If you know this and this, then you automatically know that, you know that, and that, you automatically know that. But yeah, that's kind of implied here with that was a good question, perpendicular. Yes, ma'am.
So if you got each other, does that mean they're both fingers?
Let's see. Seems like that would be, so you want 2 chords that are perpendicular to each other, and they're bisected. That's an excellent question. What do you think, girls? Let's try to make it not happen. Okay, the only way this is going to be bisected if it goes through the middle, right? Okay. So yeah, they're going to have to be both done. That's a good question. All right. Let's try that first example. Don't say it out loud. We're looking for R. Go ahead and do them both. I'll just walk around. Yes, sorry.
So a diameter basically like a special spacing chord.
Yes, it is. Yes, it is. A diameter is a chord that goes through the middle of the circle. Yep. No rounding, yes, radical form. And I think both of them will be not good radicals. Okay, you got the right triangle, right? So if it goes to the center and it's perpendicular, then remember the chord is bisected.
Okay, that helps.
She did. Yep. She did. All right. Good. Yeah, we wouldn't do that. We just leave it like that. Yeah, if it's not a whole number, then just leave it like that. Good try, though. Good try. Yeah. Yeah. So we count, right? Yeah, don't leave it like that. Yes, very nice. Yeah. Actually, we go.
I actually do, but
Actually, I kind of not go. Try to do. Apparently, you got that one?
you know, everyone's recording and Madeline here.
They're all gonna love it.
She's recording it.
And then it's on stick because we're just sitting here.
Oh,
Yeah, I forgot I was recording.
Wait, did you pause it? Can I go to the bath? It's okay.
I
Or
guess.
shall we till Ellie gets back?
Just go.
Okay, well, I'm gonna go back.
That's it.